Section 23.2, Inductors and Inductive Reactance. So the next device we want to look at is, instead of a resistor or a capacitor, what if we add an inductor? Remember, we learned about inductors when we learned about mutual induction and self-induction, and an inductor is just a coil. If you add a coil near an AC source, where the current is constantly changing, that's going to create some interesting effects. Similar to how a capacitor creates interesting effects, but in other ways, the opposite. Let's take a look. So just as we had a reactance for capacitors, we now have an inductive reactance. This is the inductor's form of reactance. And so we use the symbol L for the inductance. I'll write that out because words and terminology is important here. And the inductance is a factor in calculating our inductive reactance, which will feed into Ohm's law. This VRMS is equal to IRMS times the inductive reactance. V equals IX. How we calculate this inductive reactance is as shown, where it's the inverse of the capacitive reactance. Instead of being 1 over, it's just 2 times pi times the frequency times the inductance L. Now, since the frequency is now in the numerator instead of the denominator, instead of having an inverse graph as we did before, now we have a straight line graph. That as the frequency gets bigger, the inductive reactance also gets bigger. So inductors develop a huge amount of reactance at high frequencies and almost no reactance at low frequencies, which is the exact opposite of capacitors. What about the current and the voltage and that whole phase thing? Well, we can look at it for inductors too. When we have an inductor in an AC circuit, the current, instead of leading the voltage by 90 degrees, the current in inductive circuit lags behind the voltage by a phase angle of 90 degrees. So here, if our voltage is exactly the same, because that's created by the source, the current's always a reaction to an applied voltage. As the voltage reaches its peak, the current is again 0. That's what we saw before. But then as the voltage starts to decrease, the current increases to a positive max. So it's been shifted the other way. Now, interestingly, the average power, and thus also the average energy used by an inductor in an AC circuit, is 0. So it's not dissipating energy. It turns out only resistors are going to dissipate energy, not the capacitors or inductors. But inductors and capacitors do introduce this interesting lag. And again, rather than trying to draw the squiggles, which are really hard to keep straight, of the sine wave, we can switch to a phasor representation. So I hope you are not too phased by this. So we have our resistive circuit first and our capacitive circuit. These are the ones we've already looked at. Remember, the capacitive had the current leading the voltage by 90 degrees. In the inductive circuit, we draw our voltage again at the same point that's just set by the time and the frequency, but the current is now lagging by 90 degrees. So we would have started out in phase with it, but by adding an inductor, it is behind by 90 degrees. And this whole thing is going to then rotate around, right? Or for your view, it might look something like this. Whereas the voltage rotates around, the current is chasing it, but never catching up to it, because the two are always 90 degrees apart. But we can get the instantaneous value yet again at any point by just looking at the vertical component of each of these bits. So for the voltage, it would be this positive value, and for the current, it's going to be a negative value, because sine does go below the curve sometimes. All right, I want you to hold all three of these individual phasor diagrams in mind, because we're going to use them in the next section where in the next section, we won't just look at a resistive circuit or a capacitive circuit or an inductive circuit. We're going to look at all three put together and what happens. It's going to be cool.